Hello, everyone. Because of time zones, I shouldn't say maybe good morning, just maybe good afternoon, good evening, wherever you are living. My name is Ilker Topcu. I am from Istanbul Technical University, Istanbul, Turkey. And today I will try to make a presentation on analytic network process methods. Just an introduction. There will be a more detailed one just after me, I guess. Monica will make a more advanced ANP presentation. So let me first introduce myself. I am a professor of decision sciences in the Industrial Engineering Department of Istanbul Technical University. And I was a visiting researcher at Leeds University Business School from 1998 to 1999 and received my PhD degree in Engineering Management program from Istanbul Technical University in 2000. And I said recently, but it's almost more than 5 years. I held a visiting professor position at the University of Pittsburgh, the Joseph Katz Graduate School of Business from 2018 to 2019. And maybe some of you know I was the general chair of the 25th International Conference on MCDM Multiple Criteria Decision Making, held in Istanbul in 2015. And not surprisingly, my research interests are decision analysis, multiple criteria decision making, group decision making, but I also teach and make research on optimization, operational research, and management science. So today we will be talking about the analytic network process. Maybe you are a little bit familiar with that, maybe you have no idea about that. ANP developed by Saaty. It is one of the most powerful methodologies among other MCDM methods, and it helps us to combine the decision makers and decision analysts to combine and make evaluation of judgments of the decision makers in an effective way, and you can rank alternatives from the most preferred one to the least preferred one, or you can just make a selection and choose the most compromised solution. Although it is not written here, you can make sorting, classify them good ones, bad ones. And also you can have some predictions, estimate some outcomes, as you will see in the book of Tom Saaty. ANP is a widely used technique for structuring, modeling, and analyzing complex decisions. Actually, it's an extension of AHP, analytic hierarchy process. AHP is the most widely used method, and ANP is one of the most widely used methods, we can say. It's based on a theory of mathematics and also psychology, we can say, for ANP. And when we talk about psychology, maybe we can talk about cognitive overloads. People are not rich when they try to evaluate, assimilate large quantities of information regarding to decision problems on hand they are dealing with, they are trying to tackle. And they cope with cognitive overload, especially when there are a huge number of alternatives and criteria in the problem. And when they face with cognitive overload, most of the time they imitate to make the same decision they have made for a previous similar decision problem. Sometimes it can be called as customer loyalty. Maybe you always buy the same brand of car, we can say. One of the reasons for that can be, of course, customer loyalty, but the other reason can be without thinking the whole aspects of the problem. You can just imitate what we have done previously. Or you can just employ some heuristics to simplify the problem. Instead of dealing with the whole part of the problem, you can just look at a small portion of the problem. But this can be this can incur a drawback. You can select one of the suboptimal alternatives instead of an optimal alternative. And for this cognitive psychology, we have an experiment when you face with cognitive overload, how your brain behaves. Maybe you have heard about this experiment before. I will show you some numbers and we'll try to see how many factors can you consider at once. So let me first of all mute my phone. Sorry about that. We will do, you will see in the screen, remember, after seeing that, remember, I will one by one show you some numbers and one-digit numbers in the order they appear on the screen one after another, and I will request you to recall them. So if you are ready, we are starting first of all with 5 numbers, and then I will show you 7 separate numbers and then 9 different numbers. And most probably you will succeed and recall 5 numbers and 7 numbers, maybe 9 numbers. Most of the time participants fail with 9 numbers. We will see it now. We are starting after, remember, one by one I will show you numbers one after another. So who wants to recall them? Any volunteer? I'm checking my screen. No one? So let me do it. There's a period. But as far as I remember, it was 52734. Let's see. 52734. Now we will do the same experiment with 7 numbers. So who can say them again? Am I muted? No. No volunteer? Let me show them again. Anyone? Who wants to recall them? Everyone is muted. So I should read 1836917. So actually we are doing this experiment for seeing how our brain behaves when faced with cognitive overload, especially when 9 numbers. Let me show you 9 numbers first of all. It would not be so easy to recall them. Actually, you don't participate for 5 numbers or 7 numbers. So is there anyone for 9 numbers to participate? It was 3851623 and 9, I guess. Yeah. But it would be more easier if you try to recall them 3 digits. I mean, you can say 385, 162, and 379. It would be more easier for us. Why? Because instead of trying to deal with 9 different items, you make a trick there and you say, I am just dealing with 3 numbers, with 3 digits. This is what we say divide and conquer. We will talk about it. But first of all, let me talk about the theory behind this, 7 plus minus 2. It's based on George Miller's famous paper, The Magical Number 7 plus or minus 2, Some Limits on Our Capacity for Processing Information. Almost 70 years ago, he published this paper in Psychological Review Journal. And he said that the capacity of human short-term memory is nearly 7 separate items. It can be between 5 to 9. That's why it says 7 plus minus 2. The brain of a regular human, a rational human being, can simultaneously tackle with, analyze, differentiate, deal, process at most 7 factors, he said. And for some people, this limit can be decreased to 5, and some people, it can be increased to 9. Of course, for some exceptional people, it can be more than 9, less than 5. Less than 5 is not so good. More than 9 is awesome, we can say. That's why, especially when Tom Saaty talked about AHP, he said that in a level, we shouldn't have more than 9 factors, more than 9 criteria, more than 9 sub-criteria. Also in ANP, you will see we will have some clusters instead of levels. In each cluster, we shouldn't have more than 9 factors. If we have, then you can have some partitioning. And instead of 1 cluster, you can have 2, 3 clusters. Based on their similarities, you can connect them together. And it will be more easier to handle the problem. So first of all, for decision-making process, we have three main stages. We start with structuring the problem, and then we will model the problem, and then we will analyze the problem. So for structuring the problem, we can say that when decision makers cope with complex problems, in order to understand the problem better, not understand, but then analyze the problem better, we can say, we will divide and conquer the problem. They must break down the problem into its smaller parts. And then after analyzing each sub-problem separately, they can combine, aggregate everything together to find a final decision. And this can be very helpful as the representation of hierarchy or a network model. And as you can imagine, if you are using hierarchy, it would go to AHP. If you are using a network, it would go to ANP, based on the decision model and the relations among the factors, as we will discuss in the later slides. In a hierarchy, we assume that alternatives affect or depend on the criteria, and the criteria affect goal. Of course, your problem can be more complicated, as you see at the right-hand side. There can be some sub-criteria level. In that case, alternatives will affect sub-criteria, will influence sub-criteria. Sub-criteria will influence, affect, or depend on criteria, and ultimately, criteria will affect goal. This would be a typical decision model represented as a hierarchy. What we are assuming that criteria or sub-criteria are not affecting alternatives, or criteria or sub-criteria are not affecting other criteria, and alternatives, there are some things written to chat, but okay, it's not related with me. Criteria are not affecting other criteria, and alternatives are not affecting other alternatives. These are our assumptions. But in more complex problems, these effects can exist. They can depend on each other. If this is the case, then, we should need networks, because there may be dependencies and feedbacks. And network model with dependencies and feedbacks actually improves the importance of the criteria or the preferences of the alternatives, or in a generic form, priorities of the factors we are dealing with. That would be extracted from the judgments of the decision makers and makes our estimations, predictions much more accurate. Here you see a simple network with 4 clusters. Each set here is called as cluster. For those who are very unfamiliar with ANP, I am saying this. And all the dots here represents the criteria or the alternatives. Based on the name of the cluster, you'll understand that. And there are some arrows, as you see. They shows us the dependence. For instance, this arrow shows us the arc from cluster C4 to C2 shows us the outer dependence of the elements in C2, at least one of them here, is affecting at least one of the elements here. So we can say we will not know in detail which one affects which one, but we know that at least one element in cluster 2 affects at least one element in cluster 4. Of course, to understand in more detail which one affects which one, we should look at influence matrix. I will show you later. And this is called outer dependence. If outer dependence is in both ways, like this one, from C2 to C3 and C3 to C2, it is called as feedback. And there can be also inner dependence, like here. At least one element of C3 affects at least one element in the same cluster. It is called as inner dependence. In a hierarchy, you cannot see that. As I have shown you in the previous slide, in a hierarchy, this relation is one way. Bottom level affects upper level. This middle level affects this upper level. And finally, criteria affects goal in a hierarchy. In a network, all directions can be allowed. And let me show you some examples. For instance, this one is coming from Tom Saaty's ANP book. It is a very simple 2-cluster ANP model. One cluster represents the purpose of usage of a dam, of a water reservoir. And the second cluster shows us the water level in the dam. They affect each other. I mean, level affect usage purpose affect level. So both of them can be considered as a hierarchy. If you want to use the hierarchy here, you should have two different hierarchies. At one hierarchy, at the top, you will have goal, which level of water should I kept, then three criteria, flood control, recreation purposes, hydroelectric power generation, and at the bottom, there will be three alternatives, low level, intermediate level, high level. Or just vice versa, from bottom to up, you can have a hierarchy. The goal would be, which purpose should I select for this dam? Criteria would be low level water, intermediate level water, high level water. And at the bottom, we will have three alternatives this time: flood control, recreation, or hydroelectric power generation. Here you see another example with a marketing professor almost 20 years ago, maybe more than 20 years ago, we utilized this decision model. Cola Turkey and Pepsi Cola you are familiar with, and in Turkey at those times, just 2002, 2003, some years like that, Cola Turkey launched a national one. And we used, if you are familiar with marketing, there are four famous P's. One of them is product, you see here. Another one is placement. Instead of placement, we use distribution term. Another one is promotion. We use advertisement instead of promotion. And the fourth P, which you do not see here, is price. Their prices are very near to each other. That's why there is no price cluster here. In each cluster, there are some certain factors. And at the end of this process, ANP, we come up with estimated market shares of these three companies in Turkey. And they were very near to real market shares. And at the end of this workshop, you will see how we can measure whether our predictions are near to real values or not. It is called as Saaty compatibility index. It would be the last subject of our presentation. And when you justify your model and see, hey, my estimations are very near to real values, you can also justify the priorities, the importance of all three clusters, the factors in all three clusters. Here you see another network model. It is related with organic farming. One of my graduate students' project was dealing with organic farming. Actually, here you do not see any alternatives cluster, but strategies, policies, F cluster, or projects, E cluster can be considered as alternatives. But at the same time, besides these two, we also prioritize communication channels, distribution channels, product characteristics, product groups, and consumer buying motives. And as you see, there are some dependencies and feedbacks here, inner, outer. And we use Super Decisions software. Most of the time we are using Super Decisions software, but also you can use Microsoft Excel or spreadsheet modeling, or you can use Python. Maybe the first workshop was related with that. Thanks to Creative Decisions Foundation, this Super Decisions is a freeware, shareware program, and you can use it. And this is the website of Super Decisions, www.superdecisions.com. Now let's return back to theory of analytic network process. As I said, it is a powerful methodology. You can use it for structuring, modeling, analyzing your problem. It allows not only just one person, one decision maker, but more than one decision maker to deal with the problem, where the problem has interconnections. Dependencies and feedbacks can be aggregated, and you can say a term interconnection instead of them, or relations, you can say, among all factors. In decision-making processes, it is an MCDM method. There are lots of different MCDM methods you can utilize. But when you have a network modeling structure, one of the most convenient methods would be analytic network process method. You can use this for unstructured problems especially. You yourself will be structuring your problem, and that's why the name of the method is ending with process. Structuring, modeling, and analysis can be done. It's an approach that uses a network model, and there will be some clusters instead of levels of the hierarchy or a matrix of other methods. You'll have a network. In the network, you'll have clusters. In each cluster, you will either have criteria or alternatives, the factors related with the problem, we can say. And these are the topics we will cover today. I hope we can finish all of them. We will start with pairwise comparisons and Saaty's 1 to 9 fundamental scale. If you are not familiar with ANP but familiar with AHP, you know about these comparisons, 1 to 9 scale, pairwise comparison matrix, eigenvector, inconsistency, group decisions. But after that, we will have some special matrices which are called as supermatrix, or in long term, unweighted supermatrix, weighted supermatrix, limiting supermatrix, shortly we can say limit matrix. These three matrices are just valid for ANP method. And we will finish with Saaty compatibility index. So let's start. If you have no idea, let me introduce you the scale we are using for our pairwise comparison questions. Here, of the sub-elements, as you remember in the network, I said at least one element of this cluster is affecting at least one element of another cluster or the same cluster. If A and B, two factors, affect C, then we can ask of these sub-elements A and B, which one influences the parent element C more and how much more? Or you can ask the same question of the dependent factors A and B, which one influences C, the common factor, more and how much more? Of course, based on the wordings you are using for the factors, these questions can a little bit change, but always you will make a pairwise comparison. Which one is more effective? Which one is more important? Which one you prefer? These are the questions you can ask here. And possible answers can be given on a numerical scale if the respondent, the person you are asking these questions, is a clever guy like you and understand what is going on. You can introduce the scale, as I will introduce the scale now to you. And this is one way. If he or she has no idea about decision making, he or she cannot understand what is going on the scale, you can just say there are some possible verbal answers. Select one of them, get the answer, and you transform that verbal answer to a numeric value in the scale. As a decision analyst, you will do it yourself. There are two options here. So let's say the scale, the two elements have equal effect on the parent element means we are using 1. If first element affects the parent element moderately more than the second element affects, we will use the number 3. If this is not moderately, it is strongly more, first element affects parent element strongly more than the second one, we will use 5. If this is very strongly, we will use 7. And if it is extremely more, we will use 9. So let me repeat, 1 equal, 3 moderately more, 5 strongly more, 7 very strongly more, 9 extremely more. We are using the same scale in AHP also, but this time you say with respect to goal, which one is more important, which criterion is much more important, this criterion or the other criterion, or with respect to a criterion or a sub-criterion, which alternative you prefer. That is pairwise comparison questions of AHP. Maybe you know it. And again, these red parts are same. Equally, moderately more important, strongly more important, very strongly more important, or extremely more. But here, we are talking about influences, effects. That's why we say effects more, influences more. Okay. Anytime, if you have any questions, you can ask me, stop me, ask me. Please do not use chat because it's not so easy for me to go to chat and read it. Just unmute yourself and ask your question. We talk about odd numbers, but there are also even numbers, 2, 4, 6, 8. You can also use these numbers, but unfortunately, we do not have any verbal statement for them. If the respondent, the decision maker, is familiar with 1 to 9 scale, he or she can immediately pick an even number. Or maybe he can or she can have an hesitation here and say more than moderately, but I do not want to say strongly. Then you can pick 4, for instance. And maybe you noticed I said always first element. But what if happens if second element is more important than first, or second element influences parent element more than the first one? We will use the same scale, but this time as inverse numbers. 1 over 2, 1 over 3, 1 over 4, blah, blah, 1 over 9. Okay. So after getting these answers, we will place them in a special matrix, which is called as pairwise comparison matrix. As I have said in the beginning, this matrix is used both for AHP and ANP. These paired comparison judgments of the elements with respect to each of their parent element will be placed in this pairwise comparison matrix. Here you see an example for that. Here there are 6 criteria affecting school selection decision for your kid or for a friend's kid, let's say. Learning, friends, school life, vocational training, college preparation, and music classes are affecting our decision. And at the diagonal, we will see ones. Why? Because there is no need to ask which one affects school selection more, learning or learning. They are same. And we will fill actually this pink or whatever the color is, upper right triangle, because these blue ones would be just inverse values of that. I mean, here for this one, I guess you can see my cursor. We are comparing learning with friends. In a matrix, always rows are first element, columns are second element. When we compare learning with friends, there is no need to compare again friends and learning. If this is 3, this would be 1 over 3. If this is 1 over 5, this would be automatically 5. If this is 1, this would be 1. Okay. So you should fill this triangle, not the whole matrix. Therefore, in super decisions, in expert choice, AHP software, most programs do not show you the whole matrix. They just show you this triangle. The first column and the last row is missing in the software. Please do not panic. When you first use the software, you will not see the whole pairwise comparison matrix. Just this pairwise comparison answers we will fill. For instance, and that's why when you have n, for instance, here 6 criteria, 6 times 6, 36 entries will not be filled. First of all, diagonal will not be filled. That's why n times n minus 1, 6 times 5 we will say. And upper right will be filled. Lower left will not be filled. That's why we have over 2. So the number of questions, pairwise comparison questions we will be asking would be if 6 criteria are affecting the main concept here. 6 times 5 over 2, 15 questions will be asked. And for instance, if they say more than moderately, less than strongly, learning affects school selection decision than friends, it would be just in between 3 and 5, 4. The order of questions can differ. I am asking diagonal, diagonal, small diagonal, and then right, upper right corner. As you see, one by one, you ask these questions. Friends affect school decision very strongly more than school life effects. Here it says second element, so it would be 1 over 5. They are equal, so it would be 1. Moderately would be 3. And we fill the rest of the matrix. And as you see, here I have 4, 3, 1, 3, 4. At the first column, automatically, the software would fill, or if you are using a spreadsheet modeling like Microsoft Excel program, you yourself would write here 1 over 4, 1 over 3, 1, 1 over 3, and 1 over 4. These red values are just inverse values. It's a reciprocal matrix, we can say. And then we will extract an eigenvector. We will talk about how we can make this extraction. Software will do all the math for you, or you yourself can calculate. And let's see how we can make these calculations, especially if you are using paper and pencil solutions, manual solutions. You can use this method. This is method 3. There are 5 different methods. I will show you all of them. First of all, you sum each column. This is called as normalization. If you are not familiar with normalization, I am showing you the details. For instance, for the last column, third column, I have 3, 4, 1. Their total is 8. I will divide each value here by 8. 3 over 8, 4 over 8, 1 over 8. In the first column, total is 3.333. I will divide each value by this total. 1 over 3.33, 2 over 3.33, 0.33 over 3.33. This is called this column normalization. This pairwise comparison matrix is transformed to a normalized one. And as you see, totals are 1 now, because we divide each value by its own total, column total. And then we will get row averages, and this is the eigenvector we are extracting from pairwise comparison matrix. I said there are 5 different methods. Let's talk about them one by one. The easiest one, but which is not very near to, a little bit far away from the accurate eigenvector values, is method 1. It calculates row averages and then normalize average values. Or we can say, instead of row average, just calculate the sum of each row and normalize the sums. They would be the same, because when you get average, first of all, you sum them and then divide by n. When you divide each value by n and normalize, it would give us the same results. For instance, if you have a 4 times 4 matrix like that, and 5, 6, 7, 4, 6, and 4 are the answers, what shall we do? We will get row totals, 19, 11.2, 5 point something, 1 point something, and we will normalize it at these 4 numbers and divide each number by this total. This is the eigenvector with respect to first method. Or if you get row averages, these values would be 19 over 4, 11.2 over 4, 5 point something over 4, 1 point something over 4, and total would be 37.18 over 4. And when you make normalization, you will get the same results. In the literature, it says row average, but I am just using summation. Second method says calculate this time sum of each column, but do not normalize them, invert them, which means 1 over the value, and then normalize these inverse values. Let's see. Here, first of all, we will find each column's total value, and then invert them. 1 over 1.51, 1 over 6.42, 1 over 11.3, 1 over 18. These are the inverted values in a column vector. We get their summation, we normalize them, and this is the eigenvector. Third method I have already shown you, but for this example, let's utilize it again. We get normalization in each column, get the totals, divide each value. For instance, last one is easier to say. 7 over 18, 6 over 18, 4 over 18, 1 over 18 is the last column. And then we get row averages. This is the eigenvector. The first 3 methods are easier than fourth and fifth methods. You can do it by just using your pencil, making some subtractions, additions, divisions. But the fourth and fifth methods are not so easy. The fourth method uses geometric mean. Geometric mean of each row should be calculated, and then you normalize these values, geometric means. If you have no idea about geometric mean, I will help you. 1 times 5 times 6 times 7 in the first row. I am calculating the first row's geometric mean. We multiply each value with each other, and then get fourth root. Why fourth root? Because there are 4 items here. I mean, you multiply each item and get nth root, let's say. That is geometric mean. In Excel, there is a special function, geomean, the first 3 letters, and mean, geomean, calculates this geometric mean for you. It is 3.80638. Of course, you calculate geometric means of other rows. You come up with 4 numbers, you normalize them, add them, divide each value by the summation, and this is the eigenvector. As you see, if you have no computer, no calculator, it's not so easy for you to make this calculation. You can't find the 4th root of a number. That's why I'm saying that. And the 5th number is actually the method software uses. Theoretically, this is the most accurate one. It uses the first method, but first of all raises the pairwise comparison matrix to a sufficiently large power. For that large power, for instance, 16th power, 8th power of that matrix, we utilize method 1. After finding eigenvector, a little bit more larger power we calculate. We utilize method 1 again, and we check the latter eigenvector with the previous eigenvector. If numbers are converging, which means their values are exactly the same, you stop. Otherwise, you continue with a larger power. Let's see this in an example. This is the square matrix of our pairwise comparison matrix we use for the first 4 methods. For this square matrix, we get summations and then we normalize. This is the eigenvector of second power of the pairwise comparison matrix. Of course, it's not wise to start with second power, but I want to show you the convergence. You can start with 8th power or 4th power maybe. This is the 4th power. When you find the eigenvector, as you see, the first item is 62 something, but this is 61 something. They are not far away, of course, but they are not so near to each other. There is no convergence yet. If you utilize the same thing for 6th power and 8th power, as you see, after decimal point, if you are using 4 significant digits, they are exactly the same. And the rest of the numbers are also exactly the same, except second and fourth one. In 10,000 digits, just there is a difference of 1, which can be negligible. It means there is convergence here, and eigenvector can be selected as this one, the last eigenvector. And here you see all the results together. As you see, the first two methods are a little bit far away. Maybe we can say, we shouldn't say a little bit, very far away from real values coming from fifth method. Third method is not so converging, but it is better than among these three methods you can use with paper and pencil. Third method is the best one, but whatever you are using, it doesn't matter. For each method, rankings should be same. The highest value always belongs to first factor. Okay. So this is how eigenvector can be calculated. Another topic, inconsistency. At inconsistency, pairwise comparison matrices are multiplied by eigenvectors, and we find a new vector, and then we get ratios of each entry is here. First entry is divided by first entry, right hand side is divided by left hand side, and we have values near to n. Here we have 3 elements, so these values would be near to 3. Their averages is called as lambda max, maximum eigenvalue. This maximum eigenvalue is subtracted by n and divided by n minus 1. It is called as consistency index. And this index is divided by random consistency index. Random consistency index means pairwise comparison matrix is filled with random numbers between 1 and 9. Let's say 10,000 times, a huge number of times you do this experiment, and get averages of these constant indices of those pairwise comparison matrices filled by random numbers. And these are given in the literature. For the size of 3, random index is computed as 0.52. There is no need to make simulation and running 10,000 times again and again and find random indices. You can follow these indices given to us. And when you divide this value by that value, constant ratio is 1.76. Theoretically, it should be less than 10%. Of course, AHP and ANP are descriptive methods. They are not normative methods. You are not being forced to follow certain rules. Decision makers' behaviors are followed. Therefore, a little bit decision maker can be inconsistent. But why we are making this check? If it is more than, let's say, 11%, 13% is also tolerate, you can tolerate. But if it is more than 25, more than 20, 18%, 25%, there is some miscalculation maybe. There is some misunderstanding. Decision maker can misunderstand your question. You can misunderstand his or her response. Or when entering to the software the responses, you can have a typo. Instead of 7, you can write there 1/7. Instead of 3, you can write there 9 maybe. You are checking that. And if possible, you can ask for inconsistent responses again to the decision maker. If it is not possible, you can just eliminate that answer. Okay. And group decisions. There are 2 ways here when you have more than one decision makers. A group may be working together in the same room in a table, discuss with each other their judgments, give responses to pairwise comparison questions, and they can arrive a consensus judgment. And when facilitator, as you see there, this guy, enters their responses to the software or Microsoft Excel if they are using a spreadsheet model. But sometimes they cannot convince each other. Some can say first element is more effective. Some can say second element is more effective. They cannot give you a unique answer. If this is the case, or if you are using a questionnaire and getting each individual's opinion separately, you can send questionnaires for each respondent to give their own opinion for each judgment. If this is the case, when you collect them back, or if these decision makers on the left-hand side cannot convince each other and give you separate answers, you can use geometric mean to aggregate their results. For instance, for the example I have shown you, if mother says learning is strongly more important than France, and father says France is strongly more important than learning, in that case, in the matrix left, we will have 5. In the matrix right, we will have 1/5 for mother and father. In most societies, what mother says will happen, but in an objective way, we should combine them together. And for this combination, there will be aggregated matrix. If you use arithmetic mean, 5 plus 1/5/2 would be 2.6. But when one of them says learning is more important than France and the other just opposite, the average should be equal, which is 1. 2.6 doesn't equal to 1. Besides that, the 1/x here, the reciprocal value, will be coming from 1/5 and 5, 0.2 plus 5/2, again 2.6. This is not 1/2.6. That's why arithmetic mean fails here. But if you use geometric mean, 5 times 1/5 would be 1, square root of 1 would be 1, and also 1/x would be 1/5 times 5, which is 1, square root would be 1, and everything will be okay. So for group decisions, if you have more than one answer for pairwise comparison questions, use geometric mean to combine the decisions to get an aggregated result. And now let's skip to special matrices of ANP. Each element, we will use first of all a supermatrix, armature supermatrix, and each element will be represented at the row and one respective column. So let's say you have 5 clusters and totally 30 factors. You'll have 30 rows and 30 columns in your supermatrix. The computed eigenvectors, Birsen Karpak raised hand. You have a question? Birsen Hocam? You raise your hand.
Birsen, you're on mute if you're asking the question.
I can't hear her because
sorry about it. Yeah, sorry. Thank you, Liram.
Okay.
I don't have any question, but somebody, some other participant has, and it is in the chat. Thank you.
But I cannot see the chat. Maybe at the end of presentation.
Okay, no problem.
End of presentation, I can read the chat and give the answers.
Okay, thank you very
Here
much.
we have a computed eigenvector of the sub-elements coming from pairwise comparison matrices. They will be placed in the rows of the sub-element and the column of the parent element. That would be the supermatrix. And then we will check whether the supermatrix columns total is 1 or not, which means whether it is column stochastic or not. If there are more than 1 eigenvectors in a column, the total would be more than 1. It can be 2, 3, 4, 5, whatever it is. We should have a weighted supermatrix here, which is the normalized version of that one. Actually, there are 2 different approaches here. You can assume clusters are equally important. Just normalize them. If total is 5, you divide each value by 5. Or if they are not equally important, in that case, you should ask some pairwise comparison questions for clusters this time. Find eigenvectors. Based on the values of eigenvectors, you multiply each value with the corresponding value coming from eigenvector. I will show you in a numerical example in 2 slides later. And then when we have weighted supermatrix, we will raise that to significantly large powers to have converged or stable values, which means that, for instance, in the first row, we will always see the same number. In the second row, we will see a different number, but always it will be same. Or you can say each column of that matrix will be identically the same. That is called as convergence. So let's see all this stuff in an example. We have 2 clusters. In the first cluster, we have 3 elements. In the second cluster, we have 2 elements. And this is the influence matrix. As I said in the beginning, I will show you later. Now it's time for influence matrix. Here you can put X star plus or a letter, it doesn't matter. But if in the entry there is an X or something else, it means that row element affects column element. For instance, here A1 affects A2, A1 affects B1, A1 affects B2, but A1 doesn't affect A3. Okay. And here both way should be asked because this is direction is important. We are not asking whether there is a relation between A1 and A2. We are asking whether A1 affects A2 or not, whether A1 influences A2 or not. But there is feedback here. I mean, A2 also affects A1. But as you see, A3 affects A1, but A1 doesn't affect A3. This can happen in real life. So this is our example. Based on this example, we will extract pairwise comparison questions. How? As I said 3 slides before, eigenvectors will be placed to the parent elements column and row sub-elements rows. So here both A2 and A3 affects A1. Also B1 and B2 affects A1. We will ask pairwise comparisons of these effects. And there is an important remark here. We will not compare elements from different clusters. A's will be compared with other A's, B's will be compared with other B's. What I mean, let me show. For cluster A, we will have this pairwise comparison matrix. Which one affects A1 more, A2 or A3? That would be our question, and answer is 4. And for cluster B, we will have another matrix. Which one affects A1 more, B1 or B2? We are not comparing A2, B1, A2, B2, or A3, B1, A3, B2, because they are in separate clusters. We are comparing each element with another element in the same cluster for parent element comparison. And then we have just one effect here. A3 doesn't affect A2. We will ask no question. There is not to have a pairwise comparison matrix like that. We will omit that. For A3, B1, B2 comparison. For B1, all A's are affecting B1, so we will have a 3 times 3 matrix. And finally, for B2, A1, A2 comparison we have. And then one by one, we will calculate eigenvectors. Red values are eigenvectors. Now it is time for forming super matrix, unweighted super matrix. First of all, if there is no relation, you will see 0. This eigenvector 0.8, 0.2 will be placed here because it is eigenvector for A2, A3, their effects on A1, A1 column, A2, A3 row will have that eigenvector. As I mentioned here, there is just one effect. A1 affects A2, A3 doesn't affect A2. But if you are using, especially you are making your calculations yourself, you are not using any software, don't forget to put here 1. If you do not put here 1, it will be automatically 0, and this effect will be discarded mistakenly. You should use 1 here if you are not using software. If you are using software, it will do it for yourself. Okay, let's continue. All other eigenvectors and this one and that one will come here, and all eigenvectors are here. This is super matrix. We should check whether we should weight this matrix or not. As you see, first column says, hey, total is 2. This is unweighted super matrix. What shall we do if two clusters are equally important, A and B? Total is 2. We will divide each value by 2. 0.8 transforms to 0.4. 0.2 becomes 0.1, and so on. Second column, total is 2 again. So instead of 1 and 1, we will have 0.5, 0.5. But please be careful with the third column. Total is 1. There is no need to divide them. Our aim is having each column total S1, which means column stochastic. That would be our weighted supermatrix. So in the third column, we are not making any calculation. Similarly, fourth column total is 1. So that is the same. Last column total is 2. We divide each value by 2. And this is our weighted supermatrix. If you raise it to higher powers, this is convergence. As you see in the first row, you are always seeing the same number, 3103, 3103. Second row, 1950, 1950. Or in other words, you can say this column is always same in other columns. That is convergence, that is limiting supermatrix. These limit values can be normalized cluster by cluster. And you can see the percentages. And you can say among A elements, the most important, the most influential, the most preferred, based on the story of the problem, factor is A1. Among B, B1 influences others. Okay, is the most influential one, sorry, or the most important. If clusters are not equally important, you should ask cluster comparison questions, I said. On cluster A, both clusters are effective. A and B elements are affecting A elements. Also for B, as we have this here, A and B elements are affecting cluster B. Therefore, we should have two pairwise comparison matrices. Their eigenvectors are computed. And then, as first column total is 2, 0.8 and 0.2 will be multiplied by this 0.8. 0.75 and 0.25 will be multiplied by this 0.2. And we will have these values. At the second column, again, total is 2. We will have 0.8 and 0.2. But third column, total is 1. There is no need to use eigenvector values. You will just use the regular values, also for the fourth one. For the fifth one, again, important remark I have here. Do not use 0.8 and 0.2. For cluster B, I have this eigenvector. So first values in the first cluster will be multiplied by 0.75. Second values will be multiplied by 0.25. This is the weighted supermatrix. Again, all columns total are 1. We get limiting matrix, we normalize them. Before starting, especially I advise this for researchers, for students, before starting their job, check the convergence. What is that? Before asking all these pairwise comparison questions to the decision makers, conducting a survey, or collecting everyone to the table, first check whether your model will converge or not, whether you will have a limit matrix or not. You can assume influences of self elements on parents are equal. There's not to ask anything to anyone, first of all. This is a pre-check. And then you compute the limit matrix to check for convergence. For instance, for this one, if for each pairwise comparison matrix, you fill them with 1, 1, 1, 1, eigenvector values would be equal to each other. You can find a limit value. But let me show you another influence matrix. Number of relations are less here. Theoretically, this is not an irreducible or irreversible matrix. When you get limit matrix, as you see, there are some zeros, or there can be two patterns. We are not having convergence here. What shall we do? There are two options you can utilize. You can have some new relations. Of course, you cannot just fill some entries here and say, hey, we should have a relation. Maybe you can ask again your experts whether there is a relation here or not. Or if you are asking, let's say, 10 different experts and say at least 7 of them says there is a relation, I am putting X here. Instead of 7, you can say 5. You can decrease your threshold, your limits. And you can have some new relations. That is one way. Another way, you can assume these relations do not exist and return back to AHP. At the top, you will have a goal, 2 criteria A and B. For A, 3 subcriteria A1, A2, A3. For B, 2 subcriteria B1 and B2. I am skipping this water reservoir example you can see in my lecture notes because we do not have enough time. Here we have two clusters I already shown you. Eigenvectors are placed here. As both clusters can be regarded as alternatives, alternatives are connected to each other, 1, 1, 1 in the diagonal, you see that's the reason. And then you normalize them. This is the supermatrix. And then you get the limiting value. In the software, you will see two different numbers. One would be these limiting values. The other one would be the normalized values. In the software, you will see both of them. And our last topic, Saaty compatibility index. It is used to find how close your estimations coming from ANP are to actual data, for instance, market shares or something else. Let me show you that in a hurry. From actual data, real market shares, by making these calculations, A1 over A1, A1 over A2, A1 over A3, you'll have a pairwise comparison matrix, just an opposite reverse calculation. From your ANP model, a alternatives cluster, you'll do the same operation, but please be careful. This is transpose of whatever we have done previously. B1 over B1, B1 over B2, B1 over B3, this time comes to the column. And then you use automatic multiplication. You divide each entry with the corresponding entry of the second matrix. First row, first column is multiplied by first row, first column. Second, multiplied by second. You have 9 different numbers here. And then you get average. You get summation of these 9 numbers, divide by 9. That is Saaty competitive index. If these two vectors are exactly same, index would be 1. If it is a little bit more than 1, they are near. But if it is more than, let's say, 1.2, they are not so converging. Okay. And there is an important remark before I'm concluding. In real life, most of them, there are, let's say, 3 major players in the market, but there can be some other players and their total can be 20%. You cannot compare 4 numbers with 3 numbers. You can get rid of this part. But please be careful when you eliminate these others and just focus on major players. Their total is 80%, but the eigen values coming from limiting matrix total is 1. So you should first of all normalize here. Total is 80%. Divide each value by 80%. After finding normalized market shares, you can compare these normalized market shares of 3 major players with values coming from ANP model. That's all. Thank you for your attendance. And let me check the chat screen. And if you have any questions, how do we address inconsistency when we are using the super decision matrix? Actually, before using super decision matrix, you will use inconsistency. Dixon asked this question. Before you are skipping to super decision matrix, for pairwise comparison matrix, you will find an eigenvector. After finding eigenvector, you should compute inconsistency. You cannot compute inconsistency of super decision matrix, of course. And it's not super decision matrix, it's super matrix, just super matrix is enough. And maybe you are asking for super decision software. If it is software, in the software, at the upper right position, you can see the consistencies just above the eigenvector. You can see the inconsistencies. Any other questions? And here you can see all my contact details. You can send me email messages or WhatsApp messages. We can connect through social media. And in my website, there are some operational research and decision-making courses. Lecture notes can be helpful for you, especially if you are dealing with decision-making, AHP or ANP.
Hello, can you hear me? This is Bill Jackson.
Yeah, hello.
So when I've done this in the past, and I usually have a group of, let's say, directors, 5, let's say, and we're going and making the comparisons. If we find that one of the 5 is picking X versus Y, and everybody else is picking Y when you're doing the pairwise comparisons, we stop and ask the person, why did you pick the X versus the Y since the other 4 picked Y? And in that way, we sort of find out whether that person really knows what they're doing. And matter of fact, a couple times when I've done this, we found out that this was with some vice presidents. One of the vice presidents, after voting for X versus Y, let's say 4 or 5 times, and he was the outlier, he finally just said, I really don't understand the problem well enough to be making the judgments, so I'm going to defer to everybody else. To me, that was a very powerful thing because he recognized he didn't have the information that everybody else did, and that's why he couldn't justify why he was picking the X versus the Y, basically. So I don't know, have you gone through things like that with people?
Actually, we are having some decision conferences. In a decision conference, there are 5 or 6 different tables. In each table, there are 8 to 10 people. They are discussing with each other. They are trying to find let's say, negotiation, or they will try to convince each other, let's say. But if there is no convince, and some people say X is better than Y, some people say Y is better than X, in that case, one by one, we get individual answers and aggregate them with geometric mean in our meetings.
Yeah, that makes sense. But if you had an outlier, like I said, to me, the powerful thing is having them say, why did they pick this versus that? Because if they have to do that and they can't have the good
No, if
logic.
you have enough time, actually, as I said in the beginning, we have 5 or 6 different tables and we calculate their importances separately. and also the whole group's aggregated results. And then if there is an outlier group among all these 6 groups, we ask them to make a presentation and say why their results differ from others. And most of the time, if there is an outlier, we see that there is some misunderstanding.
Yeah, okay.
But sometimes some people can say, especially if you group people at that decision conference, hey, you marketing guys sit there, hey, you production guys sit here. Sometimes because of looking at the same problem from different points of view, their judgments can differ. But we didn't face with outlier. There can be some differences, of course, people counting in different ways, but we didn't so far get so far with an outlier very, very far away. I mean, if everyone is saying X is better than Y, the other one says Y is extremely better than X. I didn't face with such a situation yet.
Thank you.
Thank you. Any other questions? I
Uh,
guess we are over the time, but if you want, you can continue.
Yeah, thank you very much, Ilker. I think, yeah, we will have to bring the questions offline because we will have to start the next one.
Yeah, next one should start. But anyway, anytime you can send me emails or messages. You are welcome. Thank you again for your participation, and I want to thank the organizing committee for giving me this opportunity to make this presentation.
Lirong, can we stay in this one or should we move the other Zoom link?
Okay, we will bring everyone back to waiting room and we will start the next one. And thank you very much, Ilker.
Thank
So
you.
we should just stay here, okay? Am I right?
Yeah. Yeah, we can stay here, but I just wanted to find out about how to resolve the inconsistency issue with the super decision. I didn't get it very well.
Joko, I'm
Using
sorry, but we
presentation
really need to
software,
start because this is the same room for all the workshops, okay?
Okay, this is
Why
the
don't we
same room.
take it to the chat? Or
Yeah.
I
we
can
will
give
have
you
the
the
next
chat room
we
if
will
you
have the
want,
next
okay?
workshop. You can send me
Okay.
an email message. I can answer you later.
I think
All right.
Ilker doesn't.
Okay, bye.
Thank you and well done.